Okay, so now we'll have a lecture by Andy Lucas, then we'll have the poster introductions, and afterwards we'll go together to dinner. So, welcome dinner, follow us. Okay.
All right, thanks. Okay, so I'm going to sort of give two lectures that are largely inspired by this paper together with Tom Banks. The subject isn't maybe sort of 100% related to electronic hydrodynamics, but it's inspired in large part by the themes that are brought up in this workshop. So I hope you'll forgive me. Okay, so I figured just sort of to motivate why I'll talk about this subject, I would sort of briefly remind us of the name of the school. So we have electronic and hydrodynamics as two words. And what's sort of interesting is that we typically would sort of approach these problems and think about them from completely different perspectives, right? So if we take the electronic case, typically we would proceed in solid state physics by writing down some toy Hamiltonian. So let's say we have some electrons and they can hop around between different sites, and they can also interact with one another. Let me move this word over, but okay. So typically the kinds of questions, at least for this workshop, that we would be interested in are finite temperature response functions. So for example, I apply an electric field, possibly at some finite frequency, and I ask, what is the current that flows through my system also at the same frequency? And one way that you could go about solving this problem, and this is often what would be done historically, is that you would say, for example, if u is 0, this problem is exactly solvable. And then if I want to calculate this conductivity at finite u, I have to do some perturbative analysis treating u within perturbation theory. And I may need to sum up some horrible family of diagrams that may or may not be easy. And anyway, the punchline is that we sort of think about our electronic problem typically as quantum mechanical and many-body, in the sense that we really start from a fairly microscopic description. Okay. Now, the word hydrodynamics evokes a very different picture in our minds. Okay. So here we have in mind, a much simpler set of equations. These are classical equations, and I guess we heard about them this morning in their ideal form. But for me, it will be very important that this equation is not ideal. Okay. All right. And typically, we would think about hydrodynamics as being associated with fluids like air or water, which, of course, at the very microscopic level are quantum mechanical, though we rarely would think of them that way. And the idea of this workshop is that maybe sometimes these two things are equal in some limit. Okay? And this is a very interesting idea. There's a lot of profound implications for measuring response functions like this in experiment. And I think hopefully many of the other speakers will sort of tell you more details about how hydrodynamics makes particular predictions for response functions. But I thought that I would take the opportunity to instead sort of opine on some of the broader themes that are brought up by this sort of tentative equals sign. Okay. In particular, if we think about the electronic system versus the hydrodynamic system, almost every buzzword that would come to mind is the opposite between the two descriptions. All right. So if we talk about the electronic system, well, it's a quantum system, and the degrees of freedom that we write it in terms of are really, they're microscopic. This is a many-body system. Time evolution in this system is unitary, right? So I've told you what the Hamiltonian is. So the equation of motion is simply the Schrödinger equation. Okay. And this is also dissipationless. So I can run this equation forwards and backwards in time. It doesn't matter. It's just a question of whether I tell you the wave function at the earliest time or at the last time. And the one nice thing about quantum mechanics is that the equation of motion is linear. Okay. Now, almost everything about this hydrodynamic system is the opposite. Okay. So this is a classical set of equations of motion. And we've expressed these equations of motion in terms of a few degrees of freedom. Now, that's not to say that microscopically there weren't many degrees of freedom, but I've gotten rid of them for you already. Okay. Now, more importantly, this is a nonlinear system. And as we'll see, it's also stochastic. Okay. We'll come to this point in the lectures. And finally, perhaps most importantly, this hydrodynamic system is dissipative. Okay. So here, right, I can run time forwards and backwards, and it's fine. This equation you cannot run backwards in time. You will reach singularities in finite time for rather simple initial conditions. Okay. So almost every sort of elementary property of this system and this system are completely different. And so you might ask, okay, so how do we have this equals sign here? How do we compare these two things? And so, if you ask people the answer to this question, they would tell you that it's very well known how you do this. And you invoke the hypothesis of statistical physics. Okay? And that gives you, at least in principle, an algorithm to go from this many-body system to integrate out almost everything and to arrive at this simple hydrodynamic system. Okay. Now, I think that nobody really doubts that's what happens. Nobody doubts that at least some kind of hydrodynamics will emerge out of a general non-integrable quantum system. But I thought that for these lectures I would try to sort of open the hood a little bit and show you, at least part of the algorithm to really start from the many-body Schrödinger equation and step by step explain where hydrodynamics comes from. Okay? And so the goal will be essentially to take our Schrödinger equation and both making as few assumptions as possible and also at least just being very explicit about assumptions that we do make. The goal will be to get to the simplest possible hydrodynamic equation, at least by my terminology, which will be the diffusion equation for a single conserved quantity, which for me will be energy. Okay? Now, this equation is a little simpler than the Navier-Stokes equation, but already it has a number of the non-trivial features that I've highlighted. So, of course, it's classical and it only has this one degree of freedom, but it's not linear because the diffusion constant depends on energy. So it's a nonlinear system. It's certainly dissipative because, you can't run the diffusion equation backwards in time. And we actually get something that we don't often think about in classical fluid mechanics. But here we get stochastic noise. Okay? And this noise will be compatible, or needs to be compatible, with the fluctuation dissipation theorem. Okay? Now, often when people would think about what they would call fluctuating hydrodynamics, you would sort of impose this condition by hand. You would say, well, I know that it has to be true microscopically, so let me just put it in by hand. Okay. So one of our goals will also be to see that this really, it doesn't need to be put in by hand. It just comes out naturally. Okay. And some of the other questions that I hope to give either a complete or partial answer to are, firstly, this is a nonlinear system. The Hilbert space of the quantum mechanical system is exponentially large, but the equation of motion is linear. So where is this nonlinear information contained in the Hilbert space? Okay. How do we essentially take our quantum mechanical equations and reorganize them to get the diffusion equation? Okay. Another question that I'll sort of partially answer for you is, how do we know that this is the only variable that we should be keeping track of? So are we really sure that there are no other hydrodynamic degrees of freedom? I'll sort of clarify the extent to which we can talk about that shortly, because I'll actually tell you why this is the only degree of freedom. OK. So any questions so far? All right. OK. So let me sort of set up the problem. The goal today is to tell you what the memory matrix method is, at the very least. Maybe we'll get a bit farther. We'll see. OK. So let me begin, for simplicity, by thinking about a many-body quantum system on a one-dimensional lattice. Okay? And I imagine that the Hamiltonian on this lattice will be local in space. Okay? So I might have hopping terms here and here, but not all the way over here. Okay, that's forbidden. And I can do this without any. There's nothing to stop me from just binning up all of the degrees of freedom into groups, and just so everything is the same. Yeah. So here I have, 3 regions. I'm just taking all of my microscopic points on my lattice and assigning them to one region. Okay? Can do that. I'll label them with capital letters like x1, x2, and so on. And the Hamiltonian for my system, sorry, before I get there, I'll call the number of sites in each box will be L. Okay, so it's L across, and L will be large. For the moment, I'm just doing this because I feel like it, but we'll see why things become simple as we go. Okay. Now the Hamiltonian, I can think of it as a sum of 2 kinds of terms. So the first term, h of x, will correspond to these kinds of interactions. So they're interactions that lie entirely within one of my regions. Okay? And so all of the h of x will trivially commute through each other. Okay? And all of the sort of interesting dynamics is coming entirely from these boundary terms. Okay? So due to these boundary terms, the quantum problem is not separable. Okay? And they'll be responsible for all of our interesting dynamics. Okay? But we should keep in mind that just by simple scaling, h of x in d spatial dimensions, okay, will typically scale like volume, okay, L to the d. Whereas the surface term, h of xy, will scale like L to the d minus 1, just area. Okay? Yes, I only drew local interactions. Yeah. No, not for this talk. Yeah. OK. So now, suppose that for whatever reason, I told you that the only thing that you're supposed to compute in your system is you're supposed to take the wave function, evolve it forward in time, but don't give me the full wave function. Just tell me correlation functions like what's the average energy as a function of time in region 1. Okay, so for some mystery reason, this is all that I wanted to know. And as we'll see, we might as well ask the following questions because we'll get them for free. We can ask questions about what's the average value of h of x1 to the 4th or to any other power. We can get all of that. Okay. And we can also ask questions about correlations between energies in different boxes, etc. Okay. What we won't ask questions about are things like, if I have a spin flip operator somewhere in the middle of this region, I'm not going to ask you about correlation functions of that single spin. Okay. So only this information is of interest. So you might ask, well, why are you making this choice? Why am I only interested in these correlators of these energy operators? And the answer is that, historically, what we would have thought is that in the absence of any additional symmetry, I specify for you a local Hamiltonian of this form. We know that all of these h of x's commute with each other, so we can simultaneously diagonalize them. In the absence of these boundary terms, we would have a sort of integrability, so long as this L was strictly finite. Okay. Now, of course, we have these boundary terms. So even if we do happen to diagonalize all of these h of x, the actual eigenstates of the Hamiltonian will be totally different. Okay. But because the surface terms are so small relative to the bulk terms, these h of x's will last for a long time. Okay. And we can see that sort of explicitly here. So we know that these correlation functions will have some kind of slow dynamics. And that dynamics will ultimately be given by this equation. Okay. Now, you might ask, well, how do I know for sure that, let's say, my single spin flip operator doesn't also have slow dynamics? And the answer is that I won't be able to show you that in this talk. Okay. But what I will be able to show you is that this correlator and any function of energy density is not a new degree of freedom in the hydrodynamic limit. And we'll see explicitly what happens to correlation functions of arbitrary functions of the Hamiltonian, okay, or of the local Hamiltonian. All right. So with that in mind, let's just go ahead and diagonalize the Hamiltonian h of x in each of our boxes. Okay. So just some notation. The alpha of x will denote the eigenstate of h of x with energy E alpha. And the basis for the Hilbert space by this commutivity will just be a tensor product of all of the alphas. So if we want to calculate these correlation functions, this basis will be helpful. Okay. So, all right. Now, the next observation that we should make is that if we have two eigenstates that are very close in energy, we don't really care which of the eigenstates that we get, right? Because if we're only interested in this correlation function, two eigenstates that have an exponentially small discrepancy will appear essentially identical to us. So the spectrum of a single E of x will typically be extremely dense, and I just can't be bothered to draw any more lines, but these spacings will typically be e to the minus volume. Okay? So we're interested in the middle of the spectrum, or at least not the very bottom of the spectrum. So energy levels are extremely finely spaced. And we realistically don't care to discriminate between things so close together. So what we really should do is we should bin together energy levels that are not too far apart. So I'll just specify some energy scale delta and group all of the eigenstates that are sufficiently close together. Okay.
Is this levels like uniform across the energies? Or?
It's not important from my perspective. So this delta, we'll take it to scale as it won't vanish in the thermodynamic limit of L going to infinity. Okay? And as we'll see probably in the next lecture, it also shouldn't scale any bigger than L to the d over 2 without washing out some interesting physics. Okay? All right.
This e to the power minus volume, is it some sort of mini body effect? If it's a single particle problem, it would definitely not be this.
Well, yes. OK, so I'm not interested in an integrable single particle Hamiltonian. I'm interested in an honest, many body system with no conservation laws except for energy. So the Hamiltonian will have, a sort of chaotic spectrum. There, in general, won't be any degeneracies in the middle of the band, but there will be exponentially close eigenstates.
And this just comes from counting states.
Yes, it's counting. It's counting. There's nothing deep here. It's just counting. Okay. Right. And remember that once two eigenstates are within the same bin, we just say that they're indistinguishable. Okay. All right. Now that was one box, one of our x1s, but we can do that for all of them. And so at the end of the day, what we have is some number of bins. I'll draw 2 of them here. And if here's delta, 2 delta, 3 delta, delta, 2 delta, et cetera, all I care about is which one of these bins I'm in. There's a lot of eigenstates within each bin, but I don't care which one I'm in. I just want to know the bin. Okay. Now, if we have, n, right now, if we have n regions, and that's a big number, right, then this is some n-dimensional grid of which I've shown you 2 dimensions, but there's still a lot of information that we have left. So we can just ask explicitly, OK, how many degrees of freedom are we keeping track of? And the answer is, well, the number of bins that we have is, so it's the volume of each system, that's the spectrum of the Hamiltonian, divided by the bin spacing that I have. This is an algebraic thing in L, okay? And it's raised to the n power. So this is e to the n log L. So if n goes to infinity before L, which is the limit we have in mind, there's still an exponential amount of information that we have, okay? However, the total number of degrees of freedom in the Hilbert space is e to the n L to the d, okay? So even though we're keeping track of a lot of information, it's an exponentially small part of what we could have kept track of. Yeah?
If you get from the L to the D to the delta to the n to the e to the n log L without. Oh, sorry, I see.
Yeah. And keep in mind this scaling over here. Okay. All right. Good. So, OK, roughly speaking, where are we going with this? Well, the idea is that once we integrate out all of this information, we'll be able to see dissipation arise. Okay? And that's what the memory function formalism will make precise. Okay? All right. But before we get there, we need just a few more technical steps, or just notation, more or less. OK. So the idea is that, OK, the many-body wave function is, we can think of it as a sum over all possible eigenstates. So this vector notation just means, an n-component vector, okay, telling me which eigenstates I'm in. And rather than computing this, right, we don't want all of this information. This is way too much. So all we want is the following. So we want to sum over all alpha. Then we want to project into a single one of our bins Okay, so we achieve that with the following product. Okay, this just, it's a step function that forces us to have an eigenstate that lies within each bin. There's nothing fancy. C alpha t squared. So summing over all states, projecting into the bin, and asking what's the probability that we're in a given state. Okay, this is the information that we want to keep track of. So we want to keep track of essentially the classical joint probability distribution, or the joint probability distribution for being in any given bin. That's the information that we want. And I say it's classical because, well, you'll see that the effective equation of motion describing this will become classical. Okay? And I'm going to normalize this by delta to the n so that eventually when we take the continuum limit, this will really be like a continuum joint probability. Okay? All right. So now you might ask, OK, we want to compute this P of E, but have we just destroyed linearity in the Schrodinger equation? Okay? And the answer is no. And the easiest way to see that, yeah.
Sorry, before you erase that, this epsilon brings you the right computing equation.
Yeah.
Will it be probability or density or energy? Or?
So OK, if you want the spoiler, I mean, what will basically happen is that this P of E will obey a linear equation. And that linear equation is the Fokker-Planck equation for this stochastic partial differential equation. So that will be how you get nonlinearity out of quantum mechanics.
And it's a probability versus a function of
box. So I specify for you energies. You find the bin corresponding to that energy, and you measure, what's the probability that your quantum state is in that bin.
But your E is a vector, right? And this epsilon is a scalar, right?
Yeah, so this is the continuum limit of this process. So the idea is that this number of regions n will go to infinity faster than L, the size of your region. And in the long wavelength limit, there will be a universal part of this dynamics that looks like this continuum equation, coarse-grained. Okay. I'll show you explicitly how it works. Okay.
E is a vector whose components tell you which box you're in.
Yes.
Yeah,
Yes.
it's a vector, and epsilon will be a scalar, which apparently is
Yes. So okay. The way you should think about it is this is like, it's like epsilon of, I mean, other than the L normalization, it's like epsilon at x1, epsilon of x2. You should think of it as like this is a functional. It tells you, it has the data at every point all at once. So this is actually many, many more degrees of freedom a priori than hydrodynamics. But we'll see that they're actually the same. I didn't appreciate this point until after the fact, but yeah. All right, can I finish erasing? Okay. Okay. Right, so as I was saying, we want to calculate this. This has a C alpha squared. So you might say, OK, have you just destroyed linearity of quantum mechanics, which was sort of the one nice feature of quantum mechanics relative to classical hydro? And the answer is no, we have not destroyed linearity, because we can just, instead of working with the wave function, we can work with the density matrix. Okay? So if we started off in a pure state, the density matrix would just be, of course, this. But more generally, we'll actually not want to work in a pure state. We want to work in mixed states in general. Okay? So from this perspective, this is still a linear equation of motion for our density matrix. So in fact, this really looks a lot like quantum mechanics, just on a sort of enlarged Hilbert space. Okay? And we only want a sort of certain part of this density matrix. Okay? So if you think about this density matrix, in the same way that I have these energy bins over here, okay, let me sort of block my density matrix so that each block corresponds to a given bin. Okay? And now the information that I want to keep track of is any component proportional to the identity in one of the block bins. Okay? That part proportional to the identity is my P of E. Everything else in this density matrix is unimportant from my perspective. So after I block the density matrix by which bin I'm sitting in, I only care about the trace within each of these diagonal blocks. Everything else is information I don't care about. Okay? All right. Okay, so now a bit of notation, but useful notation for what we want to do. Okay? So the density matrix rho, as I mentioned, this equation of motion is linear. So it's useful to make an analogy with ordinary quantum mechanics. So we'll write a ket rho, but it has a parenthesis instead of an angle bracket to emphasize this is not in the original Hilbert space. Yes?
Could you say what justifies neglecting the both diagonal rows? Is it some decoherent processes like T1 and T2?
So there are two answers to this. So one is that I will derive for you an equation which is exact. So with no approximations, I will just tell you how these components evolve by themselves. Now, the price that you pay is that that equation is horrible and it's non-local in time. But because of linearity, I'll be able to write down something exact. So where the sort of approximation and decoherence, where these things come in is taking that non-local equation and making it simple. Okay? That approximation is, well, I erased it, but that's what's called the memory matrix approach. Okay? I should get there by the end of today. Okay? All right. So I H commute with rho. By the way, let me restrict here to Hermitian things only, just for convenience. Okay? So I, and then the commutator of H and rho. This is a linear transformation on the space of Hermitian operators, and this turns out to be antisymmetric. Okay? So rho of t, this is e to the minus lt acting on rho of 0, and this is orthogonal. Okay. Okay, to make sense of this word orthogonal, I need to specify an inner product for you. The inner product is simply the trace, okay, with this normalization. Okay. All right, so a few more technical points about going from the original Hilbert space to this operator Hilbert space. So an orthonormal basis of states for us to work in will be the following. So remember, the alpha vectors correspond to the eigenstates, or sorry, not eigenstates, but basis states in the original Hilbert space. And then we have off-diagonal things which look like this. Okay, and all of these are orthonormal. Okay. All right. Now, of course, we don't care about the density matrix overlap with all of these states. We only care about the density matrix overlap with a very special set of states. So I'll denote those states as E. Okay. So what these states are is just the sum over all eigenstates in a given bin of the diagonal state. This reproduces for me the trace in a given box. Okay. And the normalization of these states will be as follows. So E prime will be 0 unless E and E prime are the same. If E and E prime equal one another, then it's the number of states in bin E. And I'll give you two different notations for this. So first, this will just be omega of E times delta to the n. Again, this normalization is for the continuum limit. This also, just by construction, is a product of functions in each region separately, and those functions can be thought of as the exponential of the entropy. Okay, this is just thermodynamic state counting. This is the part of StatMech that we all know and love. Okay. All right. So we're almost ready to introduce our memory matrix formalism. I need to only do one more thing, and that's just define a formal projector on our operator Hilbert space. And the projector will push us onto these E states. Okay? So let me define the projector D. This is going to be the sum of over all bins of 1 over delta to the n omega E. And if I act with D on rho, what I get is delta n sum over bins of the probability that I find myself in bin E times that state. Okay? So this projector kills all of the information that I don't want in my density matrix. And so now our goal is to compute dt of d rho of t. Okay? And ideally, this right-hand side will also only depend on d rho. Then we've actually done something interesting. Okay? All right. So once we arrive at this answer, which will happen in probably 8 minutes or so, then we have done the memory matrix part of my title. Okay? But before we get there, we need a little proposition. Okay? So, okay. So for matrices A and B, I claim that E to the A plus B t equals E to the AT plus the integral 0 to t ds of E to the AS B E to the A plus B t minus s. Okay? And this sort of obnoxious identity will actually be very useful when we apply it to our problem. Okay, but first let's just prove this. First, let's just observe that it's true at time 0. Okay? That's trivial because this is 0, this is identity, and this is identity. Okay? So now that we have this, what we're going to do is take the time derivative of the left-hand side and the right-hand side and check that they both obey the same ODE. Then, because the initial conditions are the same, they're the same function. Okay, so the left-hand side, dt of the left-hand side, this is E to the A plus B t A plus B. The time derivative of the right-hand side, so here we get an E to the AT A. Here we get, well, if we take the t derivative here, we just get E to the AT B. If we take it here, we get 0 to t ds e to the as b e to the a plus b t minus s a plus b. And this whole thing is just the right-hand side multiplied by a plus b. Okay? So therefore, I've proven my, my assertion. All right.
What's the origin of this?
So, okay. If you take the Laplace transform of both sides, this is sort of a, so this becomes 1 over z minus a plus b quantity. Then you can try to Taylor expand that matrix inverse. And if you do that using some clever tricks, you arrive at this equation. Also Laplace transformed, of course. But I think it's actually more instructive for what we're going to do to not think of it that way, even though historically that's how people thought of this.
It's like you get something like a master equation for Markov chain.
Well, yes, you're getting ahead of me, but this will be where we go. Yes. Okay. All right. So now we're ready to. So now we're ready to use our proposition. Okay. And we're going to set B equal to L D and A equal to L N. Okay, so we're also going to do one more thing. This is an assumption, but it's not a very important one. Okay, and we're going to assume that we choose an initial condition that is purely diagonal. If you like, just say that we start in an equal, a mixed state, which is an equal superposition of all states in a given energy bin. Okay, so not really a physics assumption. It's just for our convenience. Okay.
I was curious, is that the point where you're not going to get possible convective terms in the heat flux equation?
So convective terms are absent because I have assumed that I don't have even an approximate translation invariance. They were lost long before this. Yeah. Okay. All right. So let's use this and our proposition. So first, so what is this first term going to be? Well, it's going to be e to the minus ln t acting on rho of 0. So e to the minus ln t rho of 0. Well, let's just Taylor expand. So 1 minus ln t plus ln t squared over 2, so on, acting on rho of 0. Now, the first term is just rho of 0. This term is 0 because I have an n acting on rho of 0, as are all of the higher order terms. So this whole first term is trivial. Yes? Oh, oops, sorry, I forgot to define that. OK, so n is 1 minus d. Thank you for reminding me. It's just the orthogonal projector. OK. Yes. All right, there we go. All right, so this first term in our proposition is kind of boring. It just returns the initial state. And at this point, we can just go ahead and say that d rho of t is rho of 0 plus integral 0 to t ds of d e to the minus ln t minus s l d rho of s. All right. Now, actually, for aesthetic reasons, I'm going to go ahead and take the time derivative of both sides. And when I do that, I will arrive at a more elegant formula, which goes by the name of the memory matrix result, or Nakajima's Wanzig formula. I don't know, whatever. When you take the derivative, you get, OK, again, if we take the time derivative here, OK, first, if we take the time derivative here, we get 0. If we take it here, then we get minus, wait, sorry, this should be a minus sign. OK. If we take the time derivative here, we get minus dld acting on rho of t. If we take the time derivative in here and add a few projectors for elegance reasons, we arrive at d ln e to the n. All right. So at this point, let's well, OK, first let me check the time. All right, so do you want me to run like 8 minutes over or end a few minutes early? I'll explain this formula, but this is a good point to stop if you don't want me to run over.
You have like 15 minutes. You started 5 minutes late.
All right, well, let's go for it. OK, so let me quickly explain, let me quickly explain this result. So what this term does is it's a local term in time. And what this says is if this L happens to rotate these diagonal contributions among themselves, then part of the dynamics is coming from this sort of internal rotation. Okay? So this is essentially dynamics among degrees of freedom that we've kept. And that's sort of ordinary. The interesting term, and this is what goes by the name memory matrix, is the second term. The memory matrix is everything except for the D row of S. So the memory matrix term, what this corresponds to is it's an interplay between essentially the degrees of freedom that we've kept and the degrees of freedom that we lost. Okay? What's happening is that every now and then we start in one of our diagonal states, and commuting with the Hamiltonian kicks us off the diagonal. And then we evolve somewhere in this off-diagonal sector for some time, and then we come back. And we have memory of this process because so far everything is exact, and we get this non-local formula in time. So because the system is linear, we were able to integrate things out exactly at the price of non-locality. Okay? All right, so now let's go and try to derive sort of our main result for the day. Okay. Now the structure of this memory function approach is very general. You can apply it to all sorts of problems, and I've done this over the years, but I thought that you can use this technique all over the place, but I have showed it to you here in the context of this problem. Okay. All right, so again, this is special to the context of this problem, but I claim that in our model, so for us, dLd equals 0. Okay? So that just kills the first term in our equation. That's convenient. So to prove this, it's pretty easy. E prime L E. Let me go ahead and define. So the operator form of this will just be a projector. This is a diagonal matrix, but it's just the operator form of this. Okay? And this is I times the trace of P E prime commute H with PE. But using trace identities, I can, up to a sign, I can move the commutator between the projectors. And the projectors are both diagonal in the same basis, so this is 0. Okay? All right. What this means is that for us, only the memory term is important. OK. Actually, let me just go ahead and, because this is going to show up all the time, let me just call this k of t, or k of t minus s. Okay. All right. So the next step is we need to figure out what is e prime k of t minus s e. If we calculated this for all e prime and e, then we would know the time evolution of our equation. Okay. So we'll do this in a few steps. OK, so first, n L E. Just by this identity, this happens to be the same as L acting on E. And I assume this notation is obvious, but there will be two kinds of terms here. One is coming from commuting with diagonal terms, and one is coming from commuting with off-diagonal terms. With inter-region terms and intra-region terms. Sorry. OK, so first, the L of x term is the following. So you can think about this operator as the sum over all of the alphas in a bin of I commute h of x with alpha alpha. And this is the same thing as the sum over alpha of I e alpha minus e alpha of x alpha alpha, which is of course 0. Okay? So this term doesn't contribute. We only get the boundary term. And I'll write the boundary term out for you. It's not difficult to show. So sum over alpha in E, sum over gamma of square root 2. Oops. Okay, so the so the LXY terms, because HXY is not diagonal in our happy basis, it kicks us out of a diagonal contribution in the density matrix into off-diagonal contributions. Actually, it's only off-diagonal contributions that you get, and they are of this form. Okay. And similarly for the n, or for Ln acting to the right on E prime. Okay. So we figured out what to do with this term. We figured out what to do with this term. So now let's talk about the middle term. Now, okay, for simplicity, we're going to belabor this middle term a little bit, but this isn't essential to the argument. Okay. So n, the key observation is that n L of xn is no longer 0. Okay. If it acts on alpha, gamma, plus or minus, it gives you plus or minus E alpha minus E gamma, alpha, gamma, minus plus. Okay? And now we're going to make a sort of, well, let's just say it's an assumption. This isn't critical for the physics that I'm going to discuss, but it will give us a happy, elegant formula. Okay? So observe, or recall rather, that commuting with h of x is going to give you a factor of L to the d, but commuting with L of xy, this is going to look like L to the d minus 1. So we expect, therefore, that E to the n ln s might approximately be E to the n sum over x L of x n s plus order 1 over L. Okay. Basically, the idea is that once you get kicked out of your sort of special diagonal state, now the fact that you're in two different eigenstates is going to start giving you phase factors as you evolve the density matrix. And the idea is that we don't really need to worry about the phase factor coming from this. Okay. The phase factor coming from just the bulk Hamiltonian is sufficient. This assumption is mathematically likely not justified, but let me not go into that in the interest of time. What I will say is that I think physically this is a plausible assumption so long as we keep in mind that we really better not trust anything in this model that looks subleading in orders of 1 over L. And I may come back to that point again tomorrow. Okay. So we should really only sort of trust the manipulations, or some of them at any rate, to leading order in gradients. Okay. All right. So, okay, so let me just write that down. Only trust to leading order in length scale. Okay. All right. Good. So with that, with this result, okay, let me not erase that formula quite yet. So we can combine everything that we have together and a few more steps that are sort of straightforward. I won't show you them. We arrive at E k of s E prime. So this is going to be the sum over, and here E does not equal E prime. So these correspond to two distinct bins, okay? And we get a sum over alpha in E, gamma in E prime, and x adjacent to y. These two regions are adjacent. And OK, we get alpha hxy gamma squared times 2 cosine of OK. And then if E equals E prime, then we arrive at E k E is minus the sum over all E prime of E k E prime. All right. Now this particularly simple formula is coming from our assumption 1, which is not 100% okay, but is pretty sensible. Yeah. But even if we didn't have a nice formula for this, we could still write it down. Okay? We could write something down. All right. So now here comes the sort of more physical assumption. So I'll say it first the way a mathematician would like it, and then I'll explain physically why we want this. Okay? So this will be, by the way, essentially the sort of many-body and non-quasi-particle form of molecular chaos. Okay. So our second assumption is going to be the following. If you take the limit as z goes to 0 plus of E L n C plus n L n inverse n L E prime, that this is finite. So in the thermodynamic limit, we want this very technical looking assumption to be true. OK, now you might ask why, where did I pull this from? So the idea is that if you look at the memory equation, which I just erased, what you'd like to do is remember sort of schematically we had this equation that was like dt rho is the integral of some kernel of t minus s rho of s. Now roughly speaking, what we want to do is take the Laplace transform of both sides. If we do that, the Laplace transform of this becomes k of z rho of z. Okay? And what we're trying to do is approximate this k of z by a constant. So what this assumption does is it tells us that our memory function is regular and that this limit, that we have a finite constant that sits here. This is essentially, as I said, the many-body analog of molecular chaos. Okay. And OK, so with that assumption, what we obtain is that dt of E rho of t is approximately, sorry, let me just rewrite it out. OK, so delta to the n, p of E t. So this is going to be delta to n, the sum over all bins that are inequivalent of w e e prime times the following. It's like an I frequency.
I frequency.
Yeah. OK. And then I'll write down the formula for W, and then we'll end for the day. OK. So this W E E prime is 1 over delta 2n times 2 pi sum over x adjacent to y, alpha in E and gamma in E prime of gamma h x y alpha squared times delta Okay. So essentially, our achievement today has been that we've started from the many-body Schrodinger equation. We've done this fancy memory matrix formalism, and then we've made sort of two more or less sensible physical assumptions, the important one being this. And we have arrived at a classical Markov process describing the time evolution of the probability of being in a given energy bin. The transition rates in our Markov equation are due to assumption 1, just given by Fermi's golden rule. Okay. So what you'll notice is that this transition rate is telling us that the matrix elements for jumping between two different bins squared times this delta function for energy conservation describe hopping of the many-body wave function between different energy bins. And all right, why don't I stop here, and if I can answer any more questions. Yeah.
If you expand the left-hand side of assumption 1 using proposition 1, like with the interaction picture, I don't see the order 1 over L. So you have LXY, all the LXY terms in that integral, right?
Okay, so you can think of this is a strict sort of, it's a perturbative statement, right? So you can think of LXY.
If you think of L as the sum of LX and LXY, then you do the same expansion that you wrote down for proposition 1, and then that O of the thing that you wrote as 1 over L. I mean, in an exact sense, that's the integral over some new time, like tau of e to the L, e to all the L of x's, like evolving the LXY term. And the LXY term is of order L to d minus 1.
Sure, but you can, I mean, the point here is essentially that if you sort of perturbed one of the other L of x's, say, you would get an L to the d correction coming from time evolution. So actually, the issue with why this is sort of a heuristic statement, I don't think it's what you've brought up. What it is that actually the matrix elements that we're interested in, of this e to the n ln s, are very close to, they're quite close to states where, well, they're on states where this difference is not large. Let me put it that way. And so strictly speaking, this is not exact. But as I said, the point of this assumption is just so that we get this nice formula. But even if you don't have this formula, this assumption is still sensible. And you would still get transition rates. You just wouldn't have a formula for what they are. So
is that like saying that the reason you get something that looks like leading order Fermi's golden rule is because the coupling terms are surface terms. So
right.
That's what makes them small.
Yeah, I mean, that's the sort of heuristic argument. But if you don't like that step, if it's not rigorous enough for you, you can throw it out.
Would sit there.
Yeah.
He would still sit,
Yeah.
Something else would say where?
in here.
This formula would be replaced by something more general, but it would still be real. This would still be a Markov process. This is the important assumption. That's all.
So what happens if you have some non-local interaction?
So, I mean, I think in principle you could carry it out. I don't want to just because, well, you'll see next time. I mean, it's not so bad to get hydrodynamics from this point. And with non-local terms, you might worry that the hydrodynamic limit doesn't have a sort of nice gradient expansion, but itself might look non-local. There's probably some Lieb-Robinson type of argument you could use to argue when it's local, but I think that's sort of missing the punchline, so we didn't do it. But yeah, I expect it can be generalized. Yeah.
Took a many-body localized system in 1D, then is it that one of the assumptions will break down, or the assumptions will work? This one breaks down for
This one fails for a localized state. You should think of this as I said, this is kind of the chaos assumption, but I've written it in a sort of strictly quantum mechanical language here. Yeah. Okay, let's say loosely speaking that would be, I expect that's true. Yes. Or maybe actually put another way, this assumption will be, or its breakdown will be important precisely on the length scales where we can't trust what we're doing anyway because it's sort of probing physics on the length scale L, and then you'll see all sorts of derivative corrections to hydro that are unphysical. So you only should trust this theory on scales large compared to your cutoff, and I suspect that's where this assumption is okay. But it's not 100% rigorous. Yes?
Can you do it for operators which are not energy, like for charge? They look like two games.
Yeah, I mean, we've done that. Yeah, you can do it. Yeah.
Okay, so let's take Lucas again.